Stoichiometry chapters, chapter 3 and 4. Let's get started. The first thing to remember is just the real basics of stoichiometry. The atomic mass, which when you look at your periodic table is these little numbers here at the bottom. They have got a bunch of decimals because they're generally an average of the different isotopes that you find in nature, whereas a single individual isotope would have a simpler number. So for example, carbon-12 would just have a mass of 12. But in nature we find that there is a little bit of carbon-13 and a little bit of carbon-14, which drags your average up a little bit. So you end up with an average atomic mass of 12.01. When you're dealing with just carbon as a random thing, then you use 12.01, but if it's more specific and you're dealing with carbon-12, you use the 12. So speaking of carbon-12, they sort of set atomic mass based off of carbon-12 because carbon-12 is this really nice kind of gorgeous symmetrical atom which has got 6 protons and 6 neutrons, and so they set one AMU equal to kind of the mass of a proton and a neutron. Nope, the average of a proton and a neutron, and so that's where we get the definition of the unit AMUs is off of 1/12 of the mass of a carbon-12 atom. So for example, if you've got nitrogen with the 14.01, you can kind of infer that most nitrogen is nitrogen 14, and there's some small amount of nitrogen that's heavier that's got an extra neutron in it, so maybe nitrogen 15, nitrogen 16, that kind of thing. Then once they had set the AMUs for the periodic table with carbon, they said, what would be really good is if we didn't have to memorize 2 big sets of numbers to do chemistry with. So let's reuse the amounts that they have for AMUs, which is the unit that we're going to use when we're dealing with really small numbers of atoms. Let's reuse those numbers when we're dealing with grams. And the way that they did that is they said, okay, 1 mole is going to be the number of atoms that we need to make 12 grams of carbon-12. That way, the 12 AMUs and the 12 grams, you can just, pick whichever unit you feel like using, and that number works both ways. So that's what they did. They said, okay, so how many atoms do you need to make 12 grams of carbon-12? That's 6.022 times 10 to the 23rd. Bam, there's your mole. So all of that stuff is based off of carbon-12, so carbon-12 is fancy and special. And that allows us to calculate molar mass when we're doing stoichiometry just by adding up the atomic masses of the elements that are in your compound. So for carbon dioxide, you add up 1 carbon and 2 oxygens, so 12.01 plus 16.0 plus 16.0, and then you get whatever the heck that is.
32 plus 12.
He's 44. Yes. So there's that. Now you have the capacity to calculate the percent composition of a compound. This is something that they used to do a whole bunch back in the day. They would say, here's a compound, I burned the snot out of it, and here are the masses that I got out of all the different elements from this compound. So percent composition, your formula, you've got your total grams of the compound on the bottom, the grams of the element that you care about on top. So it's part over whole times 100. That's your general percent formula, and that's the percentage composition of that element that you're interested in. So here's an example, which I will go and do on the black screen. All right, we have 200 grams of an iron compound is heated to drive off the oxygen. leaving only the iron. If 140 grams of iron is recovered, what percent of the mass was iron and what was oxygen? All right. So this is the part that we care about, is 140 grams of iron. The whole is 200 grams of iron. And that's times 100. And since we're going to work on our brainy math skills here, that's the same as 70 over 100, or 70%. 70% iron. Which means that you can now do the oxygen one of two different ways. You can say, well, if 140 grams was iron, then I know that 60 grams was oxygen. It's a 0. And that's 30 over 100, or 30%. Or you could have just said, you know, hey, what's left? It's 30%. And often you'll find yourself doing all these little calculations and you're like, oh, right, duh. So that's how you do percent composition, and that comes in handy pretty frequently. All right, so that's that. And then empirical formula problems. It's important to remember that when you do that burning the snot out of a compound kind of thing, and you do the percentage composition, the formula that you can get out is the empirical formula, which is the simplest possible ratio. It may be the case that the actual molecule is twice as big or 3 times as big as that. And so you have to do a little bit more work in order to get from the empirical formula to the molecular formula. What you can see here is that C8H18, which is octane, yay, gasoline. You know, 8 and 18, they have got the greatest common factor of 2. So if you burned octane, which we do, and you measured how much carbon and how much hydrogen came out and did your percentage composition and worked back up, you'd find that the ratio is 9 hydrogens to 4 carbons, which is true, but actually octane is 18 hydrogens per 8 carbons, and you have to do a little bit more work to get there. And the thing that you need is the actual molar mass, because if you know the actual molar mass of C8H18, you can look at C4H9s and go, oh, I should probably double that, and then you can double the formula. And here's an example, which I will carry out on the black screen. All right. An alcohol is decomposed and its elemental composition is analyzed and found to be, scrolling up, 40% carbon, 53% oxygen, and 6.7 hydrogen by mass. What is the empirical formula? All right. That's a good question. All right. Your first step is to take those percentages and just pretend that they're grams. Because frankly, a 100 gram sample is really easy to do math with. So from a 100 gram sample, 40% of that is 40 grams. Don't start with me. Of carbon. And then you need to convert that to moles. So grams of carbon per 1 mole of carbon. And this is a little bit of stoichiometry. Here we've got starting with what you have, bringing down your unit, and here's your molar mass equality, the number of grams per mole of carbon, which I happen to remember is 12.0 grams of carbon. So that gives you 40 divided by 12, which Senior calculator says is 3 1/3. So if you had a 100 gram sample, you would have 3.33 moles of carbon, 53.3 grams of oxygen, and same deal. And I happen to remember the molar mass of oxygen too. Hey. And 53.3 divided by 16 is, how about that? 3.33. Why are they the same?
I don't know.
It's because it's the same number of carbons as oxygens. 6.7 grams of hydrogen. And hydrogen is 1.0, which makes that math easy. I do not even have to ask Mr. Calculator. That's 6.7. So that shows you that there's a ratio of 3.33 moles of carbon. This is supposed to be an O, but we apparently don't like that. And 3.33 moles of O, 6.7 moles of hydrogen. And if you're paying attention, you'll say, hey, those are similar. And they are, because that will work out to be a pretty dang simple ratio. So divide by the smallest one. The smallest answer, this is 3.33. So divide all these suckers by 3.33. You end up with 1, 1, and 2. But it's not exactly 2. It's okay, give it a rest. So what that means is that we've got, say, carbon 1, oxygen 1, and hydrogen 2, which is sort of out of order. It looks better that way to me. CH2O, which looks like that, by the way. Remember your Lewis structures? Oh, don't forget your dots. Oh. Alright, so if the molar mass is found to be 60.22 grams per mole, what is the molecular formula? This is your empirical formula, which means that if it is the same as this, then that's the correct structure, but if it's not, then it's not. So how much does that sucker weigh? Carbon, 2 hydrogens and an oxygen, a 12, a 2, and a 16. That gives you 30 grams per mole, which is not quite big enough. It is too small by half, which means that I can tell that I need to multiply up by 2, which means I multiply my formula by 2. So I end up with C2H4O2, and that is my molecular formula, which is the actual real formula of this alcohol. And then how is this problem related to the concepts of law of conservation of matter and the law of definite proportions? The assistant is requested to not drop the equipment. The law of definite proportions says that, every time you take the same compound and burn it and look at how much of each element there is, it's going to repeat and be the same. And that's the idea behind doing this empirical formula stuff is, if it was unreliable and it was kind of randomly made with random proportions, then you wouldn't be able to do this. But because we know that it's always this way, we can do this empirical formula stuff and come up with quantitatively exactly what it's made of. And the law of conservation of matter is talking about, well, you don't have atoms, just wandering off and disappearing or appearing out of nowhere. So again, it's a reliable thing that you can do. And back to the notes. And then on sort of an unrelated topic, we have got balancing equations. We have balanced a lot of equations in the past, and balancing equations is important when you get into stoichiometry because there's one of the equalities is the mole ratio equality, which says, if I have got 1 mole of this thing, I will end up with 2 moles of this thing. Well, you don't know those numbers until you've balanced your equation. So here's an example with ammonia and oxygen, giving you nitrogen dioxide and water. Let's see if the computer will let me do this. Here we've got 3 hydrogens, 2 hydrogens. The nitrogens are balanced at the moment, so I'll let them go. I'm going to want to definitely leave oxygen till last because he's split into 2 spots, so he'll be confusing. But in order to fix this 3-2 problem that we've got going on here, we're going to need to make it 6. So that's going to be 3, no, you don't love me, do you? 3 waters and 2 ammonias. Well, now I've just screwed up nitrogen, so let's fix nitrogen. And now I can solve oxygen, which on this side we've got 4, 5, 6, 7, which is delightful. And the way that you solve that is you go, haha, 7 halves. And then you go and you double everything. So you end up with actually 4, 7, 4, and 6. And the answer is, do you remember who came up with the law of conservation of mass?
I don't remember.
Oh, you should. I know. I think it was Lavoisier. Let's hope I'm right too. One thing that we haven't done before that they do expect you to know how to do on the AP exam is to split up the ions when you're writing out reactions between ionic compounds, particularly in aqueous solutions. So the very familiar hydrochloric acid neutralized by sodium hydroxide is written this way, which is kind of funky, but it makes sense because they have, in the aqueous solution, they have dissociated. So hydrochloric acid, it's a strong electrolyte, it dissociates 100%. So really what you've got is hydrogen ions and chloride ions and sodium ions and hydroxide ions. And then what ends up happening when you mix those two together and they react is the hydrogen and the hydroxide get together and form molecular water, so they're not being ions anymore, so they get to stay together over here. And then the sodium ions and the chloride ions just hang out, which is interesting because the other thing that they expect you to notice is the dudes that just hang out. A net ionic reaction, a net ionic equation, is writing these ionic equations and then crossing out the dudes that don't do anything. So that's supposed to be an A. Kinda pointless. And so what that becomes is the actual reaction part, which is hydrogen ions and hydroxide ions become water. It's very popular and type of format of writing chemical equations on the AP exam, so you have to be used to it. And you have to be careful because they'll try and trick you into writing it out like this the long way, when what they will give you a point for is the net ionic equation. So if it doesn't really say anything, it sort of wants the net ionic equation. All right, what do we got? Scroll down. We have some practice problems. So now is your chance to take a break here and go and work your practice problems. And then we will come back and show you the answers. And we're back, and you're done with your problems, and now I will do them too. For the molar mass of magnesium phosphate, you need to know the average atomic mass for magnesium, which is 24.31, and yes, we are going to be using hundredths this year. Why did I start with 3? I don't know. Don't start with me. All right, and then phosphorus, 30.97. That's 2 times 30.97. And oxygen is 8 times 16.00. And you add all those suckers together, and I got 262.87 grams per mole for magnesium phosphate. Here we have copper sulfate pentahydrate. That's going to be 63.55 for copper, 32.06 for sulfur, for oxygens, 4 times 16.00, that's going to be 10 times 1.01 for hydrogen, and 5 times 16.0 for oxygen. And you add all those suckers together, and I got 249.71 grams per mole. Okay, hopefully you got that, or I'm wrong. We'll see. All right, what is the mass percent of each element in HClO2? This is going to be part over whole, so let's go ahead and calculate what the whole is. There's 1.01, there's 2 times 16.00, and chlorine, I believe, is 35.45. You add all those together, and I get 68.46 grams per mole for the whole compound. And then each of those 1.01 grams per mole of hydrogen, 35.45 grams per mole of chlorine. And 32.00 grams per mole of oxygen. And you divide those out and multiply everybody by 100 so that you get the percentage. And I got 1.48% hydrogen, 51.78% chlorine, and 46.74% oxygen, which when you add all of those together, if they add to 100%, it means that you did it right, and I think that they do. All right, number 3. A molecule with a molar mass of 119.37 grams per mole contains 10.05% carbon, 0.85% hydrogen, and 89.10% chlorine. What is the molecular formula of this compound? All right, you pretend first that your percents are grams. So 10.05 grams of carbon, 0.85 grams of hydrogen, and 89.10 grams of chlorine. Then you convert everybody to moles by bringing down your units like good children. And that's 1 mole of carbon's mass. Grams of hydrogen is 1.01. And grams of chlorine is 35.45. For that, I got 0.8375 moles of carbon, 0.84 moles of hydrogen, and 2.51 moles of chlorine. But Mrs. Gunlock, your sig figs are all messy right now. It's okay, I'm not done with the problem. Then you divide by the small one. On all 3 of them in order to get the ratio to be pretty. That gives you 1, 1, and 3, which gives you the empirical formula, CHCl3. And then, so that's my empirical formula. How about my molecular formula? So I need to add up my molar mass and see how much I need to multiply by. So 12.01, 1.01, and 3 times 35.45. And when you add those all together, you get 119.37. But that's the same number. So what do you multiply by? By 1. That's right. So this is both your empirical and your molecular formula, which is a possible thing. Number 4. write the molecular complete ionic and net ionic form of the following equation. Aqueous sodium hydroxide reacts with aqueous phosphoric acid to give water and aqueous sodium phosphate. But I don't remember my polyatomic ions. Told you to memorize them. All right. Sodium hydroxide, sodium, and hydroxide is OH minus, so with Na plus you end up with NaOH. Aqueous phosphoric acid, phosphoric, 8-ic, us, that's going to come off of phosphate, which is PO4 3 minus. So you cross those and you end up with the formula H3PO4, and that gives you water. And aqueous sodium phosphate, which is Na3PO4. We need to write little X on these. Now, water is not aqueous, it is liquid. And we need to balance 3 sodiums, 3 hydroxides, 3 hydrogens. Now we're gorgeous. All right, so that is my molecular equation. Now for the complete ionic form, that's going to be 3 sodium ions and 3 hydroxide ions and 3 hydrogen ions and 1 phosphate ion yields 3 waters and 3 sodium ions and 1 phosphate ion. And it turns out that some of these are worthless ions, also known as spectator ions, because they're just sitting around watching. And the dudes that qualify are the sodiums, sodia, and the phosphates. So they get crossed out, so we end up with 3 hydroxides and 3 hydrogen ions, giving us, wait a minute, this is what the example was like. Yeah, well, this is also a neutralization reaction, so yeah, you're going to end up with the same deal. Notice that this is 333, so we actually should reduce it. It's a good arrow. And that's it. Bam.